Hello and welcome to the second video of the M2 chapter Work and Energy. Question on the screen here to review the previous video. A package of mass 1 kilograms is pulled 2 meters at a constant speed up a rough plane inclined at 20 degrees to the horizontal. So at 20 degrees, here's our package, 1 kilogram, so the weight is just G, and it's being pulled up at a constant speed 2 meters up the plane. The only resistances to motion are those due to friction and gravity, so we do also have friction here, and of course the pulling force, pulling it up the plane. The work done by the force is equal to 10 joules. Note that's the work done by the force, not against gravity or against friction. That's the work done by this force here. Calculate the coefficient of friction between the package and the surface. So first I'm going to split the weight into its component parts. Here we've got G cosine of 20 degrees, and then down the plane here, G sine of 20. So in the previous video we did an example where we used the weight of the force to find the work done against gravity, and we used the friction to find the work done against friction, but in this question the work done is by this force, and this force, if it's moving at a constant speed, which it is equal to the friction plus this component of gravity here. So P is equal to the friction plus G sine 20, and this is the force we know the work done for. Quickly find friction on the side. I'll call this R. So the friction, if it's moving, is equal to mu times R, and we know R is equal to G cosine 20. So I can put that in here. We know the pulling force is equal to mu G cosine 20 degrees to balance the friction, plus G sine 20 degrees to balance the component of the weight down the plane. We also know that the work done is 10 joules and the distance travelled is 2 meters. So the work, which is 10, must equal the force P times the distance is travelled in the direction of that force, 2 meters. So P must equal 5. So all of this thing here has to equal 5. Now we can rearrange to find mu. 5 minus G sine 20, all divided by G cosine 20. And that, if I put that on my calculator, will give us mu. And that is 0.1789, which to 3 significant figures, 0.179. I would have done 2 because we've used G, except that it specifically says in the question 3 significant figures. In this video, we're going to calculate kinetic energy and potential energy. When a particle moves, it has kinetic energy. This is calculated with the formula half times mass times the square of its speed. It's worth noting that this is a scalar value. Even if you thought of this as velocity rather than speed, by the time you square it, you can see very easily kinetic energy is always positive. It doesn't give any indication of whether you're traveling forwards or backwards. There's no direction involved. It's just a scalar quantity. When a particle does work against gravity, it gains gravitational potential energy. From a chosen level, where h is equal to 0, you need to specify where that is. This is calculated with the formula that we've seen before, mgh. The work done that you do against gravity, lifting an object up, gives it gravitational potential energy, so that when you drop it, that gets transferred into kinetic energy and it falls back down to the ground. A couple of quick notes here. Gravitational potential energy is often shortened just to potential energy in mechanics, because this is the only type of potential energy we're going to look at. So if you do physics and you're thinking, wait a minute, potential energy might mean elastic or gravitational or electric, in mechanics it always means gravitational. So you'll see me writing PE and referring to potential energy. That means gravitational potential energy in all of these videos. The second thing, very important, is this bit here. From a chosen level, potential energy is relative to a chosen point or a chosen level where h is equal to 0. If you've got a particle that is above that point and you're using this as your 0 level, then it has positive potential energy because H from the 0 level is considered positive. However, if you're below that level, although we can't have a negative distance, we can have a negative displacement, just indicating the direction. And that's similar here. We can't really have a negative energy, but it's just indicating the direction. Negative potential energy is just saying that it is below your 0 level. From question to question, when you're using potential energy, you will need to decide for yourself, if the question doesn't tell you, where your 0 level is going to be. Quick example, a particle of mass 0.5 kilograms is moving at a speed of 7 meters a second. Calculate its kinetic energy. So we've got the formula, kinetic energy is equal to a half mv squared. We know the mass, and we know the speed. Put that into your calculator, and we get 12.25. And this is energy, so that's joules. Second example, a container of mass 25 kilograms is lowered vertically to the ground through a distance of 7 meters. Calculate the loss in potential energy. Potential energy is equal to mass times gravity times height. And here's an example I think where it's pretty obvious. It doesn't really matter where you choose your level to be 0, whether it's here or whether it's here. You're talking about the loss in potential energy, so you're going to be giving a positive value and calling it a loss either way. What I mean by that is we're effectively using a change in height, so it doesn't really matter where your 0 level is. 25 times 9.8 times 7. And when I put a change in height there, that now is a loss of potential energy. That is 1715 joules. Worth noting, this could also be gain in potential energy with a change in height here if it was going from here to here. I'll just finish this off. I've used 9.8, so I will round that to 2 significant figures. Third example. A parcel of mass 3 kilograms is pulled 10 meters up a plane inclined at an angle arctan 3/4 to the horizontal. As I've said on some previous videos, this is telling you tan theta is 3/4. From there you can work out sine theta is 3/5, cosine theta is 4/5 using a little right-angled triangle. The parcel is being pulled up a plane inclined at theta, and it's going 10 meters up the plane, and it has a weight of 3 times g. Now we want the potential energy gained by the particle. So the potential energy is equal to mass times g times h. Similar to the previous example, the gain in potential energy is a relative thing compared to where it is. So it's mass times gravity times the change in height. And this is the change in vertical height. So from here to here, I want this distance, which is 10 sine of theta. We know sine of theta is 3/5, so that's 6 meters. Back to the formula. Mass 3 times g 9.8 times the gain in height 6. 176.4 to 2 significant figures, 180 joules. So those are some examples just using those 2 simple formulas for kinetic energy and potential energy. But there's a close connection between work done and kinetic energy that you need to be aware of. We can use constant acceleration to derive an equation that connects these 2 ideas. What we do is we start off with F equals ma, and assuming constant acceleration, we can also use the formula v squared equals u squared plus 2as. Rearrange that to give a equals v squared minus u squared over 2s, and substitute that into our F equals ma equation. So the a becomes v squared minus u squared over 2s. Now if I take the s up on the other side, we get F times s equals mv squared minus mu squared over 2. And just taking those apart, we get half mv squared minus a half mu squared. And the reason to do that is because we get Fs, force times distance, which we know is equal to work done. On the other side, we've got these two expressions here, which we can see is kinetic energy, a half mv squared, that's the final kinetic energy, and a half mu squared, where u is the initial velocity, that's the initial kinetic energy. So this expression, the final kinetic energy minus the initial kinetic energy, is the change in kinetic energy. So we can see that the work done is equal to the change in kinetic energy. So if a force does work on a particle, it might increase the kinetic energy if the work done is in the direction of motion. If the work done is against the direction of motion, it's doing work against the particle, and the kinetic energy will decrease. And it's always interesting to consider the units. So we've got force times distance, which is our Newton meter, which we know is a joule on the left-hand side. On the right-hand side, we've got the kinetic energy. Mass, which is kilogram, times meters per second for velocity, squared. So we get kilogram meter squared over second squared. Then if we take kilogram meter per second squared, the meter per second squared, that's acceleration. Kilograms, that's mass. Mass times acceleration is a force. So we get a force there, which is newtons, and then there's still a meter left over, which is Newton meters, which of course is joules. So that's a little units-based explanation for why kinetic energy is indeed joules, and work also in joules there connects through this equation. We'll finish with two examples that use this connection. A box of mass 2 kilograms is pulled across a smooth horizontal surface by a horizontal force. The initial speed of the box is u meters per second, and its final speed is 2.5 meters per second. The work done by the force is 3 joules. Calculate the value of u. From the connection that we just saw, we know that work done is equal to the change in kinetic energy. The work done, we're told, is 3. That is equal to a half mv squared minus a half mu squared. We know v is 2.5, and we also know that the mass is 2. So it's just a case of rearranging the equation, which gives us u squared is equal to 13 over 4. So u is equal to root 13 over 2. And that is the speed, so that's meters per second. 1.80 in decimal form. Final example. A van of mass 2,000 kilograms starts from rest at some traffic lights. After travelling 400 meters, the van's speed is 12 meters per second. A constant resistive force of 500 newtons acts on the van. Calculate the driving force, which we're going to assume is constant. So we've got a van. My van looks suspiciously like a box, I know. Just makes it easier to draw. 2000 g for the weight, although we're going to be using the mass. Initial speed 0, final speed 12. Distance between them 400 meters. The forces, we've got a constant resistive force of 500 newtons. There's no element of the weight because I've assumed it's on a horizontal ground. And of course the driving force from the engine. Using that same connection, we've got work done is equal to change in kinetic energy. Of course, the change in kinetic energy is quite easy. Here there is 0 kinetic energy. So we've got a half mv squared. The work done has two elements, the work done by the driving force and the work done against resistance. I'll do them both together by doing d minus 500 as our overall force, or the resultant force. So the resultant force times the distance travelled would be the same as doing the driving force times the distance travelled, that's the work done by the driving force, minus the work done against resistance because it's in the opposite direction. Whichever way you think about it, you can see obviously they're the same thing. So that is equal to 1/2 times the mass, 2000, times the final speed 12 squared. If we put all of that on a calculator, I get the final answer 860 newtons for the driving force. I hope that's enough now for you to have a go at some questions in exercise 4b, and maybe I'll see you in the next video for some conservation of energy.